We've all heard about the current global warming trend, climate change, and what's causing it, CO2 increases in our atmosphere. Well, CO2 and methane and other greenhouse gases. But how exactly does the greenhouse effect work? This is just going to be a short video kind of explaining the concept behind the greenhouse effect, what gases are greenhouse gases and are currently contributing to the greenhouse warming that we're experiencing on Earth today, and how the greenhouse effect operates on other nearby planets to Earth, as well as how it's operated and changed throughout Earth's history. First things first, Earth's climate system, and pretty much any system that involves temperature or heat, involves some sort of energy balance. So in other words, when something has more heat than its surroundings, the heat will flow from it to the surroundings until the energy is in balance. For example, if we put a cup of hot coffee on a table, it will lose heat to the surroundings until it's room temperature. Likewise, if we put some iced coffee on the table, it will gain heat from the surrounding. The surroundings will provide it heat until the ice melts and it becomes room temperature once again. So things become in balance through this transfer of heat from system to surroundings and vice versa. And Earth is the same. Earth is a system with heat input and output. And when we're talking about heat input and output, solar radiation is the major input of energy to Earth. It is mainly visible and UV radiation, which are just wavelengths of light, which then Earth, heats up from and converts to IR radiation, which it emits back out, and that's the output. If you didn't understand that, don't worry, I'm going to explain all that in just a second with actual diagrams. But in any case, it has solar radiation input and heat output. And if the amount of energy that Earth absorbs from solar radiation equals the amount of energy it reflects and emits, then its temperature would remain constant. In other words, if the in equals the out, the energy is balanced. There's energy balance in that system. And this is sort of how Earth works. Solar radiation is the input of energy to Earth, and IR radiation is the output of energy that Earth emits after it heats up. All this means is that the wavelengths of light that are emitted from Earth's surface, or the wavelengths of radiation or energy, are longer than the ones that it absorbs. It absorbs UV and visible light from solar radiation, sunlight, and it then heats up and emits infrared light. Everything that has heat on Earth emits infrared light. We emit infrared light, which is why we can use infrared or thermal cameras to see that we are red in those cameras compared to our surroundings, which are blue because they're colder and we're hotter, and we're emitting IR radiation. We talked about this in the atmosphere video. Essentially, Earth absorbs solar radiation and emits IR radiation. So in equals out, right? Not necessarily. If this were the case and the in of energy equaled the out of energy for Earth, Earth's average temperature would be about negative 17 degrees Celsius or 0 degrees Fahrenheit and remain constant. But its current actual average global temperature is about 16 degrees Celsius or 60 degrees Fahrenheit. So why didn't this work? Why didn't our simple model of the in energy and the out energy for Earth work or come up with the temperature that Earth actually is? Why is it warmer than what we calculate using the in equals out energy balance model or idea? Because this model neglects the existence of Earth's atmosphere, and Earth's atmosphere greatly affects this in versus out ratio. This is because Earth's atmosphere contains gases that block outgoing IR radiation. These are called, you guessed it, greenhouse gases. Gases like water vapor, carbon dioxide, methane, nitrous oxide, and many other types of gases in the atmosphere block outgoing IR infrared radiation, but do not block the incoming solar radiation. Therefore, they decrease the amount of outgoing energy from Earth, but they don't affect the incoming radiation. Therefore, we will receive the same amount of incoming radiation. The in stays the same, but the out is less, meaning that in does not equal out. In is actually greater than out, and that leads to a rise in temperature. Thus, this explains the higher actual temperature of Earth compared to what we would calculate if Earth did not have an atmosphere or did not have the greenhouse effect. And despite the negative connotations surrounding the greenhouse effect currently on Earth, it is actually really important. It is essential for life on Earth. If Earth did not have its greenhouse effect, again, it would be closer to that temperature we calculated based on the N equals out scenario, about negative 17 degrees Celsius, which would mean that Earth's water would not be liquid at the surface, it would be frozen, and that would limit or completely wipe out any possibility of habitability on Earth. Well, probably not wipe out, but it would be really a lot harder for life to be present on Earth, and it would probably be a lot smaller, microbial, non-interesting life. Well, okay, I shouldn't say that. I actually love microbes, but it wouldn't be, huge multicellular or intelligent life by any means. We could see systems where there's frozen water at the surface, like Mars or Europa, where, there's a possibility of life, but it would be way greater if those systems had atmospheres and greenhouse effects strong enough to support liquid water at the surface of those planets or moons. So, do other atmospheric constituents affect climate, or is it only greenhouse gases? Well, the major constituents of Earth's atmosphere, nitrogen and oxygen gas, which make up about 99% of Earth's modern atmosphere, do not actually interact with incoming solar radiation or outgoing IR radiation. So they don't really affect the in and out energy balance as much as greenhouse gases do, which is why we tend to focus on greenhouse gases when it comes to atmospheric constituents that cause global temperature changes on Earth. So now let's rethink our model while considering the atmosphere. Because, greenhouse gases do play a big role, but they're not the only thing in the atmosphere that affect the in versus out scenario. For example, there is, a lot of incoming solar radiation that is reflected off of surfaces like clouds and other atmospheric particles. Therefore, the in is not unaffected by Earth's atmosphere by any means. It is reflected and decreased by these particles and cloud surfaces, and combined with the amount that's reflected from Earth's surface, like off of snow or ice caps, this makes up about 31% of the total input or incoming solar radiation that is reflected and kind of doesn't even, ever get absorbed by Earth to begin with. So it doesn't even go into the in versus out scenario because it's never absorbed and therefore never re-emitted as IR radiation. Then the remaining solar radiation input is absorbed either by particles in the atmosphere or by Earth's surface. And then, of course, once Earth absorbs this solar radiation, it heats up, and then because it heats up, it emits IR radiation, and of that IR emission or radiation that radiates back outward towards space, about 83% of that on modern Earth today, based on its current atmospheric constituents, is blocked by greenhouse gases. The figure actually that I'm using doesn't even match perfectly with the numbers I'm presenting. For example, the total surface absorbed IR radiation is about 160 watts per square meter, which compared to the incoming 340 is like 47% instead of 49. So every source has slightly different numbers. In any case, what you might notice by this chart is that 398 watts per square meter of outgoing IR radiation is higher than the total incoming solar radiation number of 340, which you might think, well, shouldn't the outgoing number equal the in, at least before the greenhouse effect? But keep in mind with this number that this number is higher because it's not only taking into account the initial incoming solar radiation of 340 watts per square meter, it's also taking into account the recycled IR radiation or thermal energy that's being recycled back to and through Earth's system as greenhouse gases, do their thing to heat up the atmosphere and other Earth systems. So this 398 number is kind of taking into account both incoming solar radiation and blocked outgoing IR radiation, not just the incoming, if that makes sense. In any case, the greenhouse effect is not unique to Earth. It operates on all other planets too. Well, all other planets with atmospheres that contain greenhouse gases. For example, Venus has a very thick atmosphere and very rich in CO2, which again is a greenhouse gas. And because of this, it has a very strong greenhouse effect. It's also closer to the sun, so it already receives more input of solar radiation. And because of this, it has a surface temperature hot enough to melt lead, which is really terrifying. And then we have Mars, which is just, a little bit further out from the sun than Earth. But it does have an atmosphere, and it is rich in CO2. However, the atmosphere is thinner than Earth, and it has no water vapor, which is another major greenhouse gas for Earth's system, at least. But because of these differences, its greenhouse effect is not as strong as on Earth, and thus Mars is pretty cold. Only frozen water is present at the surface, at least today. Obviously, many projections suggest that this was not always the case, and it might have had a thicker atmosphere in the past that did promote liquid water at its surface, and potentially abundant life, who knows, but today it is definitely not an ideal greenhouse effect scenario for at least habitability on Mars. This is why Earth is kind of considered in a Goldilocks zone for a lot of things, not just like solar input, but like the greenhouse effect and its atmosphere and everything. And also just in time, it's in a very Goldilocks zone of time too. With that said, even Earth's greenhouse effect has changed drastically in intensity with time throughout Earth's history. For example, events like Snowball Earth were exacerbated by snow cover and albedo. In other words, they were glaciation events that nearly covered all of Earth in ice, and they were very much exacerbated or worsened by the fact that the snow cover and ice cover blocked incoming solar radiation more and more the more that it expanded. And so that was a big feedback mechanism that led to the intense spread of ice on Earth. But these events were initially caused by major carbon burial from photosynthesis and weathering, which I talk about in my Snowball Earth's video. But in any case, essentially what this means is that carbon was taken from the atmosphere from photosynthesizers to a much greater extent than it had previously been on Earth, and that caused this big shift in the carbon cycle that led to a lot of the carbon in the atmosphere going into rocks or the geosphere, which led us into this huge cooling event because that, obviously removed a lot of greenhouse gas from the atmosphere. Whereas the equal and opposite is true for periods where there was intense carbon release to the atmosphere or carbon addition to the atmosphere. For example, times when there were major volcanism or impacts that impacted carbonaceous sediment and released a lot of carbon and other greenhouse gases to the atmosphere led to intense warming events like the end Permian mass extinction with major volcanism, or the KPG mass extinction that took out the non-avian dinosaurs with the impact, and similar to today's sixth mass extinction with humans kind of acting as the volcano. Ultimately, though, the carbon cycle is cyclic, thus balance is always eventually restored. In other words, during periods like Snowball Earth or the end Permian mass extinction, where carbon in the atmosphere drastically decreased or drastically increased, eventually that was brought back around because eventually the carbon, is cycled back through the atmosphere or back through the geosphere, and everything balances back out from there. But when there are periods of rapid climate change, that balance often doesn't come back without major biological devastation, aka mass extinction events. Remember, in some of my recent videos, I've been talking about how rate is different than magnitude, or not different than, but more important than when it comes to causing mass extinctions through climate change. In other words, when there's gradual climate change over millions of years of timescales, life has a chance to evolve and adapt, whereas when climate change is rapid in Earth's history, it does eventually balance back out, but this rapid change typically causes mass extinctions first. And yes, life does recover after the fact, but not the same life. So it's not necessarily in our best interest to sacrifice ourselves for the next biodiversification event. But in any case, rate is dangerous, and that's what we're dealing with right now. For example, today, rapid warming due to carbon emissions will eventually be balanced by carbon burial back in the geosphere, largely because this increase in CO2 in the atmosphere causes negative feedback mechanisms, in other words, mechanisms that reverse the trend, because this increase in CO2, for example, causes an increase in primary productivity and photosynthesis, which eventually will cause, again, the buildup and burial of carbon in the geosphere, because these organisms take up carbon from the atmosphere, photosynthesize, and cause organic carbon to become buried and preserved in the geosphere. But this takes like millions of years, so it's not a fast effect, but it does eventually happen. And other negative feedbacks occur, like weathering. Intensified weathering occurs when increases in atmospheric CO2 occur, because there's more acid rain, more chemical dissolution and weathering of rocks, which transports ions to the ocean that lead to the burial and preservation of inorganic carbon, like calcium carbonate minerals as well. So there's a lot of negative feedbacks operating that will eventually balance out the current trend in the carbon cycle, but these occur over millions of years, and in the meantime, they're having other side effects, like 1, the actual warming is one thing that's not great, 2, ocean acidification, and 3, ocean anoxia, and there's others, but these are the main 3 effects of modern climate change that are devastating current ecosystems and leading to major extinctions of many species that are not great. However, there are ways in which we can increase the rate of these balancing processes, like weathering, for example, or even this primary productivity negative feedback. And I talk about these, for example, in my carbon sequestration or ocean fertilization video. I'll link one up here, which these might help us in more quickly reversing the current trend and limiting extinctions. But of course, it won't prevent them completely, because they're already happening.